Welcome back to Module 4, Working with EEG Data. And this is the last lesson for Section 2, which is about motor imagery. So as we already know, processing EEG signals involves decomposing the signals into different frequencies, amplitudes, and phases. This can be accomplished through many methods, one of which is the Fourier transform. So some key questions that we'll try to address: how can we apply this knowledge to understand motor imagery? What are the critical steps for analyzing brain-computer interface signals? And what is the power spectral density? Alright. So one of the critical steps in the design of BCI applications based on EEG is the processing and analyzing of such signals in real time in order to identify the mental state of the user. The signals that come from the brain are noisy and non-stationary and very complex and with high dimensionality. Therefore, identifying some mental state requires specific signal processing techniques and machine learning tools once you acquire the signal. The first step is the signal acquisition, and we need to acquire the signal by using an electrode signal, where we have the International 1020 system, which states how to configure the electrode position in order to identify the readings coming from the neurons. Between signal acquisition and feature extraction is pre-processing, which we just talked about. So the feature extraction is the next important step, because you need to select some features that is very important in identifying some mental state. And some mental state example can be fatigue or imagining a movement, such as in motor imagery, such as moving your left hand or right hand, etc. And you need to select the features because you will need to essentially classify them. So you need to assign a class to a set of these features extracted from the signal. And then this class corresponds to the mental state identified. So why classify the features? Well, because sometimes the final application is not only identifying the mental state. Maybe you want to control a device such as prosthetics, video games, other brain-computer interfaces, etc. So you must identify some features and then classify them in order to detect or identify these kinds of mental states. So this is the process of a brain-computer interface when you need to acquire the signal and you need to select the features and then classify them. So this kind of classification requires machine learning tools such as SVMs, neural networks, and all other algorithms you want to use in order to identify the mental state. So this device control can give us feedback for designing various neurotechnology applications. So let's consider a motor imagery application. So the two mental states that we're going to identify are imagining the left hand movements on one side and imagining the right hand movements on the other side. So the person is trying to think about left or right hand movement with the electrodes on the scalp, and once you have placed the electrodes, then you'll acquire the EEG signals. Then we need to interpret and manipulate this signal in a digital domain. So we're going to use a computer, which is what the name brain-computer interface comes from, and we need to use a computer to extract the features that can be important for us to identify the mental state. Once you extract the features, then you need to classify them using machine learning. Then once you classify them, you would use it in a motor imagery application with an estimated class, which you can use for controlling a robotic arm, for example. So the filter digital signal can be used as a command to control an electronic device. Alright, so how do we extract these features? One of the most widely used methods to analyze EEG signals is to decompose a signal into 4 different frequency bands, typically. And you need to identify the power, or how much delta you have in a signal, or how much beta you have in a signal, and so on. And in this case, this implies that the composition of the signal is made up of frequency components, which are the features that you're going to extract from the EEG signal. And then you would classify them. And the power of each frequency band will tell you something about the mental state. And in spectral analysis, it is common to obtain the power spectral density for the EEG signal in this case. So before we define the power spectral density, we need to know what would be the autocorrelation function is. So for our autocorrelation function of our real and stationary signal, let's say we have x of t, which is the sequence or the data of an electrode. So x of t is the signal sequence. The autocorrelation function is defined by our x of t, and this is the expected value between the multiplication of x of t and the same signal, but moving forward through time by tau steps. So you basically multiply both signals, which is the same, but one of them is moving towards the time domain, and then you need to average them. So suppose x of t is this, suppose x of t is just this square signal, which just shows like ones and zeros. So if you want to make the autocorrelation for this signal, it implies that this signal, x of t, is going to be multiplied by itself, but let's say you move tau steps. So say, let's start with this one, and if you multiply the blue and black signal, which are the same signal but a different time step, it would give you 0 at this time step because there's no similarity. But once you move the signal here, let's say it's x of t, which is black, it remains static. Yeah, so the original data is black in this figure, and it remains static the whole time, and you're moving the signal. So the blue signal is like sort of like the kernel, and you move it by tau step. And at this time, you will have a 0.1 in here, since like 1 times 1 is 1. So at this tau step here, it will give you 1. Now, let's say we have the blue and black signal overlapping with each other. So here you need to sum all these points and then average them. And at the end, you will have this point equal to 2, and so on. So as the function moves forward, the result will decrease again. So the final result of the autocorrelation function would give you this some kind of like triangle because you're moving through time. And this signal multiplied by itself but moving forward through time will give you like this kind of relationship. So this peak of the triangle means that at this time you'd have the highest value of the signal, so it tells you how similar is the signal. And in EEG signal, the autocorrelation function would be helpful to determine the power spectrum density in this case. Another side note is autocorrelation is a signal being multiplied by itself, but if you multiply it with other signals, then it's called cross correlation. And the power spectral density denoted as S of x will equal the Fourier transform, which is just an integral, and it is the integral from negative, it's not written here, from negative infinity to positive infinity of the function, which is the Rx tau times the complex component, which is the exponential 2 pi if tau, which with respect to tau. So this would give you the power spectrum of the signal. So if you try to determine what would be the power on each frequency band, it will tell you something about the mental state that you want to describe. So how should we compute the power spectral density? There are a lot of methods, and one of the most widely used one is the Welch method. It consists of averaging consecutive Fourier transforms of small windows of the signal. So let's say that we have this original signal, and we need to determine the Fourier transform of small windows of the signal. So the window is called the Welch window, which is just like a Gaussian. And then you're moving forward in time, and then you're sliding the window, and probably you will have overlapping or no overlapping. And once you average all of the Fourier transforms, it gives you the power spectral density, or the PSD. EEG data is like always EEG data is always time varying. So the signal is likely to look like a perfect sum of pure sines. So this is the reason why you're going to use windows for averaging Fourier transform, because this signal is not just the EEG data, and it's not just the sum of pure sine waves. So since the EEG signal is very noisy, so trying to identify the window size would give you a better resolution. So in this case, you would need to identify the size of the window in order to identify the power or the better spectrum that you're going to use at the end. So how do we find the optimal window duration? The commonly used approach is to take a window sufficiently long to encompass at least two full cycles of the lowest frequency of interest. So for instance, in EEG data, there are 4 frequency bands like delta, which is 1 to 4 hertz. The lowest frequency one is like just 1 or 0.5. So some literature says 0.5 is the minimum frequency of the delta band. So to determine the window size, you'd have to use 2 full cycles of the lowest frequency of interest. So say we have T, and T would equal to 2 divided by the minimum frequency, so 2 divided by 0.5, so time duration would result in 4 seconds. So this window is basically sliding over time and averaging the Fourier transform of these segments. So this is the method to basically determine the power spectrum density. So briefly, for implementation in Python, you can import using from the SciPy import signals so that you can use the Welch method. You're going to determine the power spectrum of AF3, which is one of the electrodes of the EEG. So you need to define the array and the data length and the sample frequency. So the sample frequency may depend on the EEG headset. So in this case, it's like 128 hertz divided by 2, since the Nyquist frequency tells you that you need to sample minimum twice the minimum frequency that you have on the signal. So 128 divided by 2 will give you 60 hertz, and that maximum frequency that you can have in your recording will be 60 hertz. So Python is helpful to construct the power spectrum and the frequency vectors by using signal.welch, and you need to pass in the argument, the electrode array, the sample frequency, and this last argument is the window size. And so in the previous slide, the window size is 4, and here you can use the window size of the whole length of the recording, so you need to cover the whole sequence moving forward in time. So the result would give you something like this. You can plot frequency versus power spectrum density, and that you give the power for the frequencies. So you can see here that 0 to 5 hertz, which is like the delta frequency band, gives the highest power. Then 5 to 12 hertz, which is theta, has like lower power, and alpha is even lower, and you barely have beta in here because it went past like the reference, which is 0. So it means there's a lot of like power in like lower frequencies in this data. Right. So if you have high power in delta, delta is like the slowest of the brain waves and takes place during our deepest dreamless stages of sleep. So, excuse me. So you need to identify which electrodes work with delta. Or you can identify alpha, which is the default state when your mind is physically and mentally relaxed. So for each electrode, determine the power spectral density and see which electrodes you notice the highest delta, or the highest alpha, or the highest beta, and so on. So you can do this while, say, you do an experiment in motor imagery, or identifying a mental state of a video gamer while playing a video game, and so on. And if you record different signals for each electrode and determine the power spectrum density of each electrode, you can get valuable information from their brain activity. So these are the features that you can use for classification methods, and so you can utilize machine learning tools to detect the mental state that you want to identify. All right, to summarize this another very long lesson. EEG signals can allow us to understand the brain activity that occurs during motor imagery. This is accomplished through using Welch's method to determine the power spectral density. And what's next is analyzing EEG data in Python notebooks. So yeah, that's it for section 2. So I'll see you in the next section.